very much, and thank you very much to you who stayed around in the afternoon to this last talk. I'm very grateful to the organizers to have this opportunity to speak here at the EHS. And I will try to connect with Francis's talk in the morning. And after Ruth has showed you in the previous talk some other approaches and ideas on how to tackle Feynman integrals, I want to go back to the parametric representation that Francis showed you in the morning. And actually, Francis put forward at the time very new approach to the computation of Feynman integrals, which uses hyperlogarithms throughout and is one attempt and one way to understand the prevalence of multiple polylogarithms and MZVs in the calculation of many Feynman diagrams. So I want to talk about Feynman integrals, but specifically their connection with hyperlogarithms. And the motivation for this particular approach is, or the goal is to understand why are so many Feynman integrals just abbreviate by Fi, expressible via multiple polylogarithms and Francis already showed you these functions in the morning. I just recall briefly. So these are functions which you can define like the multiple series I just write down now. So they're indexed by a bunch of integers and 1 to nd, and they depend on several complex variables. And one way to define them is via this summation over nested integers k1 up to kd. And then the thing you sum is just the monomial indexed by this summation indices in the parameters divided by the summation indices raised to certain powers as dictated by the index of the multiple polylogarithm. So we have seen already some examples also in Ruth's talk where these functions show up in Feynman diagram calculations, and it's still today sort of mysterious why there's so many of them where this is the case. But you also know, remember, not all Feynman diagrams or Feynman integrals are of this form. We know explicit counterexamples, and we have many conjectures of graphs where we are pretty sure that they're of a much more complicated form. And if you think of the whole world of Feynman diagrams, you might actually say probably this is a set of measure 0 in whatever kind of measure you put on the set of Feynman graphs. But the surprise is that for most things which are relevant for physical calculation, it's actually you get already very far with just these Feynman diagrams. But still understanding why they are of this form is very difficult. And I will try to demonstrate to you one approach which at least in some cases makes it very clear why this is the case. And I try to be very explicit and very down to earth, so I decided to take an explicit example that we have seen already and try to compute it from beginning to end. So if anything is unclear in the meantime, please interrupt me, because it should all be first or second year calculus, I hope. But it's still interesting because you see what's actually the important ingredients why this approach works. So the idea that we want to follow is take the parametric representation and integrate out one Schwinger parameter at a time. So recall that we had parameters associated to each edge of the graph called alpha e, when we did the Schwinger trick. And then we had the parametric representation. And I will consider an explicit example, the wheel with 3 spokes. Which was the first non-trivial example that Francis mentioned in his outlook. So what was the wheel? It is this graph. So it is a wheel. It has 3 spokes. Let's call these edges 1, 2, 3, 4, 5, 6. As you can think of it as a graph in phi to the 4 theories with 4 external legs, but because it's logarithmically divergent in 4 dimensions, it has this residue, which I will denote by I of this graph, which is just the integral over omega g divided by the square of the graph polynomial, the first semantic polynomial. And what did this mean? I will evaluate this integral finally, so we just have to integrate from 0 to infinity all the Schwinger parameters. Well, not actually all of them, because remember in this form it's a projective integral. So when we make it affine, we can restrict an arbitrary hyperplane, and I will choose the hyperplane in the form that I just set alpha 6 to 0. So I will integrate 1 over psi g squared, but I set alpha 6 to 1, sorry, not 0. So this is the integral we want to compute. And recall that by definition, this semantic polynomial psi g was the sum over all spanning trees. And each spanning tree contributes a monomial, which is the product of all edges not in the spanning tree. So in particular, this is linear with respect to each individual variable. And this means that the first integrations are essentially elementary. So how does this work? We want to compute its amplitude. Let's just do the first integral over the first variable from 0 to infinity of so over alpha 1 over psi g squared. I just reminded you that this is a linear polynomial. So let's just say that I call psi upper 1 the coefficient of alpha 1 in this polynomial and psi lower 1 the constant part. And this integral is clearly trivial to do. So we just have the primitive of the integrand. And we have to evaluate this at 0 at infinity. And we just get the 1 over the product of psi upper 1 and psi lower 1. So this was easy. At the next stage, we have to leave the rational functions. So let us compute the next integral over alpha 2, psi upper 1, psi lower 1. Now these are coefficients of the original polynomial, which was linear in each individual variable. So these polynomials are still linear in the next variables. So we can do a similar decomposition, d alpha 2. And I just continue with this labeling scheme. So I call psi upper 1 to the coefficient of alpha 2 in psi upper 1, which is a polynomial depending on the other variables. And psi upper 1 lower 2, the constant part with respect to alpha 2 in the polynomial upper 1. Yeah? So these are just shorthands for particular spanning trees which contain edge 2 but not edge 1, or which contain neither of edge 1 and edge 2 and so on. Yeah?
There is no quadratic term that will appear in this exponential.
So I started with a linear polynomial. I had a complete square. So I just get the coefficient of alpha 1 times the constant part. So this is a quadratic polynomial, but it's factorized in 2 linear forms.
Depends on alpha 2 to the alpha
Yes.
6. Okay.
So these are polynomials here. So psi upper 1, psi lower 1 are the coefficients with respect to alpha 1. So they are still polynomials in the remaining variables. This is important, yeah.
But when we make the expression in the second integral, we are
Yes.
not going to have the quadratic term in alpha 2.
No, because these are linear polynomials in the variables. They are linear in each variable. I start with a polynomial which is linear in each variable, and I pick a coefficient. So it's still linear in all the other variables. That's the important point. So I only have linear terms here. Psi lower 1, upper 2, alpha 2, and the constant part. So how do I do this integral? Well, I do a partial fraction decomposition. So I get a prefactor from the partial fraction decomposition, which you can work out very easily. And then we're left with the integral over alpha 2. So I hope you can all believe this formula. And now we can just compute this integral in terms of logarithms that evaluate at 0 at infinity. And then this thing here just becomes the logarithm of psi upper 2 lower 1 and psi upper 1 lower 2. And in the denominator we have the other two coefficients, psi upper 1 2 and psi lower 1 2. So what we've seen here is that we can very easily integrate the first two variables. And at that stage, the partial integral we have computed so far is the logarithm of some coefficients of the graph polynomial. And it has a prefactor, which is given by this polynomial from the partial fraction decomposition. Now, the idea is to continue with this and integrate out one variable after the other. But in general, now we're in a difficult situation because this is now genuinely a quadratic polynomial. This is before because we multiplied two linear things. And if we want to integrate again, we would like that this is actually continuous factorizing in these linear forms as we saw here. So let us have a look what this actually is in this case. So what is psi upper 1 lower 2? I want to integrate alpha 3 next. So let's decompose this with respect to alpha 3. So first of all, this is the coefficient of psi which of alpha 1, where alpha 2 is set to 0. So it is the sum over all the spanning trees which do not contain edge 1, but which do contain edge 2. And if you think about it, this actually means that this is the ordinary graph polynomial of the graph where you delete edge 1 and where you contract edge 2. This is a so-called contraction deletion formula. And if you take the graph, delete edge 1, but contract edge 2, what happens is that 6 and 4 become parallel. I have 6 and 4 parallel. And you still have 3 and 5 in the business. So this is actually this graph polynomial. But I want to see how it depends on alpha 3, just for the fun of it. So I know this is linear in each variable. So what is the coefficient of alpha 3? Well, it's again the spanning trees which do not contain alpha 3. So I can just delete edge 3. And then I'm essentially left with a one-loop graph. And we know from a one-loop graph, we just get the sum of all the edges in the loop. And then we have a contribution where alpha 3 is 0. So I have to contract alpha 3. So this gives me the graph polynomial of the sunrise, which we have seen, with the edges 4, 5, and 6. Just as a reminder, this was the symmetric polynomial in two variables, which you have seen already in Francis's talk. Now we can
contracted that edge 3 at this time, does it?
Yes. So I do the decomposition with respect to alpha 3. I look at the coefficient of alpha 3, and what happens when I set alpha 3 to 0. So I contract alpha 3, and then everything becomes parallel. Now we can just do the same game the other way around. So I delete edge 2 and contract edge 1. Then 5 and 6 become parallel, and 3 and 4 remain. And again, I can delete alpha 3 also. Then I have only alpha 5 and alpha 6 remaining in the loop. And I have the same, when I contract 3, I still get the same sunrise polynomial. I don't bother writing the indices here. And we also have upper 1, 2, which means that I delete both edge 1 and edge 2. Well, what happens then is that you have this lonely 6 hanging around, and the edges 3, 4, and 5 remaining. This is just a one-loop graph, and I just told you that you just have to sum all the variables in the loop to get its polynomial. Then the last guy is the one where we set alpha 1 and 2 to 0. So we contract both edges alpha 1 and alpha 2, which means that the edge 3 is now both endpoints of 3 are now connected, because if we contracted 1 and 2. This looks a little bit odd. So we have this vertex where now edge 3 is like a self-loop. And then we have the sunrise of 4, 5, and 6 here. But what does the self-loop mean? You're summing over spanning trees. I mean, no spanning tree can contain edge 3, because then it would have a loop. And the spanning tree is not allowed to have a loop. So actually, no spanning tree contains alpha 3, which means that alpha 3 actually multiplies this polynomial. It's the divisor of the polynomial. And then the thing that remains is just, again, this sunrise polynomial. Again. So you will soon see the reason why I wrote it this way. So what is actually this denominator? We want to understand this quadratic polynomial here. So what is it? Well, let's collect the terms quadratic in alpha 3. So we get terms quadratic in alpha 3 from the product of these two minus the product of these two. So from this product, we get just alpha 4 plus alpha 6 times alpha 5 plus alpha 6. And then we subtract the product of these two, which just gives the sunrise. Then we have terms linear in alpha 3. But here, the terms linear alpha 3 come from multiplying a psi with such a term. And also here, from the subtraction term, the term linear alpha 3 is this times this. So actually, all these terms are divisible by the sunrise graph polynomial. And we get alpha 4 plus alpha 5 and 2 alpha 6 from these. And then we subtract alpha 4 and alpha 5. And then finally, we have a constant part, which is just the square of the sunrise polynomial. And now you see that actually these cancel. And what is this polynomial? I wrote it down here. So if you multiply this out, the only thing that remains here is alpha 6 squared. So what you find is
maybe each time you write this sunrise polynomial, it can take different variables.
It's always the same. I was just lazy. It's always 4, 5, 6.
Because it's a very different permutation of that.
Yeah. I mean, it's symmetric. It's a symmetric polynomial of the 3 variables, 4, 5, 6.
It's always the same variables.
You left out 1 to it.
Yeah. I have only 4 variables remaining, and I explicitly looked what happens with alpha 3, and 4, 5, 6 remain. So we observe, so there's a miracle happening here, namely that this thing actually is a complete square, which you can see over there. So it's just alpha 3 times alpha 6 plus the sunrise polynomial squared. And this thing inside the square is again linear in each variable, because we know that psi itself is linear in each variable. So this is a complete square. Of course, there must be some explanation for this. And this is an example of so-called Dodgson identities. And these identities follow from the fact that the psi polynomial can actually be written as a determinant of a matrix. And then there's a whole theory of identities between them in terms of so-called Dodgson polynomials, which is something that also Francis and Karen Yates worked out in great detail. You might know Mr. Dodgson is also known as Lewis Carroll. Double L, I don't know. So this is the wonder of Alice in Wonderland, if you want. The point is that these factorizations are extremely important for the fact that we see these multiple polylogarithms in so many places. Because if this would not happen, if this would just be a generic quadratic polynomial, then in order to continue the integration, we would have to take the roots of this polynomial and introduce algebraic functions already. But because we have a complete square, we can just integrate by parts. Yeah, so if we integrate by part, we get one term where we just integrate the complete square and we keep the log, but just evaluate it after 3, 0 at infinity. And we get other terms where we have to integrate still, but the log became rational. Then we do again separation, partial fraction decomposition, then we again get logs. But the point is, we don't get a dilogarithm. Yeah. So in the next integration, because of this complete square, we remain in the world of logarithms and elementary functions. And the result of this, that the period or the residue of this graph, you get because of this integration by parts, you get actually several terms, but you can rewrite them with a symmetry, and you actually see that you can write 3 times the same integral, which in terms of alpha 3, yeah, 4, and then the sunrise polynomial and a logarithm. 4 plus alpha 5, alpha 4 plus alpha 6 over this sunrise polynomial. Yeah, this is an easy exercise to do this calculation that you get this expression. The point is that because of this complete square, we didn't get a dilogarithm at this stage. Now I want to write this out explicitly. So remember, we have 3 variables left, alpha 4, alpha 5, alpha 6, but alpha 6 is set to 1. So we are actually only left with a 2-dimensional integral. And I will just rename the variables. So alpha 6 is 1, alpha 5 I call y, and alpha 4 I call z. And this is the integral 0 to infinity dy over y. And you can do the partial fraction decomposition here, which I already did for you here in this expression. So we get so this comes from the sunrise polynomial if you do these substitutions and do the partial fraction decomposition. And then here we just get, this is now called z plus y, z plus 1, and y plus 1, z plus y over y plus 1. Okay. So we boil down the computation of this integral to do this 2-dimensional integral over logarithm. And we again see, there were already Dodgson identities at place in the first thing that I showed you in detail, but also in this integration by parts procedure here, we have to do new partial fraction decompositions, and also there you actually make use of Dodgson identities. So the observation here is that again everything is linear, everything factorizes into linear functions in the next integration variables. Yeah? So if you now integrate z, everything is linear, and then with respect to y, and also the arguments here are linear and z, so everything looks very linear. And where is the... But of course, at this stage now, we have to introduce more general special functions because we cannot compute this integral in terms of classical logarithms and rational functions anymore. So we do need a dilogarithm. But the question is, how do you represent these polylogarithms? I've just erased the sum representation because we don't want to work with the sum here. We want to have an iterated integral representation. So we want to exploit the iterated integral representation of multiple polylogarithms. So multiple polylogarithms are not only sums, but you can also write them as iterated integrals. And so for this, let us take a set of points in the complex plane. It should be a finite set. And we think of, or we call these elements of this set singularities or letters. But I want to write them with a special symbol. So I introduce symbols omega sigma, which should indicate that this is actually representing a differential form for all these letters. So this is an abstract alphabet. And then we can define special functions for each word in this alphabet. Define
Sigma is no more the domain of integration. Sigma was upstairs the domain of integration.
this is a capital sigma.
Oh, no. In the integral, IG.
Yeah.
But I mean the element.
Oh yeah, so sorry, yeah, this is a different sigma, yeah. Sorry. Then we define the hyperlogarithm LW of Z associated to a word W in A star. So W is just a sequence of these letters by the following rules. First of all, if you have a string of omega zeros, this just should be the powers of the logarithm of Z, the normalization by n factorial. And then we also want that if you take a hyperlogarithm which has a word which begins with some letter, and then there come some other remaining letters, that this first letter tells you the differential behavior. So this should be 1 over Z minus sigma times the hyperlogarithm associated to the tail of the word. So this is just the reverse way of writing down an iterated integral. But it does not fix the constant of integration, of course, which we require now, such that the limit when Z goes to 0 of these hyperlogarithms is 0 unless the word is of the form omega 0 to the n. So if you have a string of zeros, we just fix them to be the logarithms, which of course diverge quite mildly at 0. But for all the other hyperlogarithms defined in this way, we should think of them as iterate integrals from 0 to Z. So in fact,
can we have an example now?
Sorry?
Can we have an example?
Yes, sure. That's exactly what's going to happen next. So example, well, what happens if you just take one letter? Well, then this is just the integral from 0 to Z of dt over t minus sigma. And because the integrand is given by the differential behavior, but it also has to vanish, so sigma is now supposed to be non-zero, has to vanish at Z equals 0, so it's this iterate integral. And this is just the logarithm. Z minus sigma over minus sigma. I want. Then there is L omega 0 omega 1 of Z. What does this look like? Well, we have to integrate from 0 to Z d t1 or t1 minus 0. Yeah, this is the last integration. When we differentiate with respect to Z, we have to get down this. And then we have the integral the nested integration dt2 with t2 minus 1. And if you recall, Francis briefly mentioned the iterated integral representation from Li2, so this is actually minus Li2 of z. And quite generally, when you have L, you have a bunch of zeros. Oh my goodness. Sorry, I'm changing orders now. So people familiar with MZV will know this inside out. So I take a word, but I have to make distinctions whether a letter is 0 or not, because it's treated differently in the setup. So let's suppose I have a word which ends in a non-zero letter, then there comes a bunch of zeros, then there comes a non-zero letter and a bunch of zeros, and so on. So I have d non-zero letters, and each of them might come with some zeros. Then this is actually the same as minus 1 to the d times the multiple polylogarithm with these indices evaluated at the ratio of the non-zero letters. So we get all the multiple polylogarithms just in a particular representation. This is the point. Of course, the benefit of writing them in this way is that it is trivial to integrate in this representation, because we just define them as the iterated integrals. So if we just continue our example over there, let's just rewrite this logarithm here as an iterated integral in this form. So we just have to look at the arguments of the logarithm. So this integral 0 to infinity dz 1 over z minus 1 over z plus y over 1 plus y. This logarithm so this is nothing but L omega minus y, and I have the logarithm with singularity at z equals minus 1, and I have in the denominator the logarithm which has its singularity with respect to z at minus y over 1 plus y. Now I made sure that I have the right differential behavior. I also have to think if I fix these constants correctly, which do not depend on z, but I know if I take the logarithm here and set z to 0, then I just get y in the numerator, and I also just get y in the denominator. So this vanishes at z equals 0. And these are also defined to vanish, so this is the correct expression. And now if I integrate, just by definition, it just means that I prepend an omega 0 and an omega minus y over 1 plus y to get a primitive of these, and I evaluate at infinity. So in this language, this just means the following. So I introduce a shorthand notation. I want to write linear combinations of words in the arguments. And I just define this by linear extension. Now I just have to prepend this combination of letters. So what I did now, I expressed the penultimate integration in terms of an iterated integral evaluated at infinity, but it still depends implicitly on the remaining integration variable y, which I still have to integrate. So if we want to continue in this way, we first have to understand this function as an iterated integral of y. So I hope this is clear. The idea is that at each stage in this process, we want to express the integral, the integrand, as an iterated integral, namely a hyperlogarithm, in the next integration variable. Unfortunately, I don't have enough time to do this in all glory detail, so I have to take a little shortcut here. But it's actually quite simple how to do this. So there is a little lemma which you can prove. suppose that we take a hyperlogarithm of some word at some argument, that might be infinity, like in this case, and we compute its total derivative. Yeah. In the case where these sigmas are considered as functions. So they're not fixed. We really compute the full total derivative. And you can actually prove that there's a simple explicit formula for this. You have a sum over all the letters, and you take the word where you delete one of those letters, and then you have an explicit logarithmic total derivative of the consecutive differences of the letters. Yeah. So the proof is differentiate under the integral and integration by parts. But it's really a very simple exercise to do this. There are some boundary terms in this formula, so there's a sigma 0 appearing here, which is defined to be z, and a sigma n plus 1, which is defined to be 0. These correspond to the boundary terms of the integration. So actually, this is a totally symmetric formula. Now, with this formula, if you apply the total derivative now to such an expression, you see this grading by weight, this recursive structure, which is so special about multiple polylogs, coming into place here. Because if you apply the total derivative, on the right-hand side, you only have lower weight multiple polylogs, which have one letter less, and explicit logarithmic derivatives. Now, in our case, these letters here are rational functions of y. So if you compute the logarithmic derivative of the rational function, you just have to factor the rational function into into the zeros and poles with respect to y, and we get a hyperlogarithm. The differential form is defining a hyperlogarithm. So this looks good. And for this piece, which in this case would still be a logarithm which remains, we can just apply the machinery recursively. So I just give you an example here, but I won't work it out. Yeah, I just tell you. So this function here, if you do all this, it's just you can write it as in a hyperlogarithm with respect to y. So the point is that now all the letters are independent of y. So you can convert this representation to this, and this is algorithmic. There's no magic in this process. But now the final integration is trivial, right? Because we just have to integrate. We have to multiply this with 1 over y and integrate from 0 to infinity. So this just means that we have to put another omega 0 in front. So we finally arrive that the residue of the Beer with 3 spokes graph that we started with is 3 times this thing. So we have now an iterate integral of weight 3. And as a hyperlogarithm, it has this form. Evaluated at infinity, which still might look mysterious, but what is it? I mean, this is an iterated integral. On c minus 0 and minus 1. So we immediately know that it is a multiple zeta value. You can also think of it as a period of M06 And if you want to write this as a multiple zeta value, you just use Möbius transformations, for example, or associators which relate infinity to 1 in some way. So we can apply the Möbius transformation, which sends z to z over z plus 1, which means that the boundaries, the upper boundary of infinity is now mapped to 1, 0 stays 0, and you can compute the pullback of the differential forms under this Möbius transformation, which is a simple exercise. And if you plug this all in, you get that this is the same as the integral omega. Did I do this correctly? Omega 0, omega 1. This is now a hyperlogarithm evaluated at 1, which is essentially a multiple zeta value. There's still a little thing with the regularization you have to do because it starts with 0, and you can use a shuffle product. But if you use this, you can show that this is the same as you have. If you multiply this out and do this little thing, which I don't have time to explain, but it's really not that difficult. You can rewrite it in this form. And if you just take the definition of the multiple polylogarithm, how they relate to these hyperlogarithms, namely this formula, I see that this is essentially Li3 and this is Li1, 2. So this is 3 times Li3 of 1 plus Li1, 2 of 1, which is 6 times zeta of 3. Okay. So I spent an awful amount of time on explaining this first non-trivial example, but I hope it was at least understandable to some degree. The amazing aspect of this calculation is that it gets you ridiculously far in practice. So at least in some families, for example, these single-scale massless 5⁴ integrals that Francis was mentioning, this is a case where we have, I would think, the best knowledge concerning the expansion in the loop number, how far can we get and still compute a lot of integrals. This is really outstanding compared to other kinematic configurations, which can be much more complicated. And so we know we already have 2 loops where we get elliptic things, these massive sunrise diagrams. But in these massless diagrams, following these lines, one can get quite far. And the basic idea is exactly the same. So let us recap what we did. We computed partial Feynman integrals, meaning I call this I index k, or Francis calls it I index k, which still depend on the remaining variables from k plus 1 up to the final variable. So integrate from 0 to infinity the first k variables. And let's say we just compute such a residue. So we compute these integrals one at a time. So at each step, we just integrate the next variable. The prerequisite for doing this is that we can express these functions as hyperlogarithms, right? I was only telling you how to manipulate hyperlogarithms, but in many cases, in the complicated ones, the Feynman integral is not expressible as a hyperlogarithm, and at least not in the Schwinger parameters. And maybe it's not even a sensible iterate integral in any kind of form. But in the case where this works, we can just apply this procedure which I outlined to you. So the prerequisite for this to work is that all singularities of this function, which is a multi-valued function of these variables. So there are some devices, there's some variety which describes where this can pick up monodromies. But we need that all of these singularities are linear in the next variable. Alpha k plus 1. Because if this is the case, then I just sketched you an algorithm based on this lemma and another lemma which tells you how you get the boundary constants. There is an algorithm which in this situation can transform a representation given in such an implicit form into a representation which is explicit in y. And then we can just find a primitive by prepending letters or doing integration by parts, and we can compute the Feynman integral. So the message is that all this will only work in very special situations, but if it works, the whole procedure is automated, it is implemented in computer programs, so we can try to focus our attention on the actual geometry which sits behind this computation. So the actual integral itself, what happens here, what are the precise polylogarithms which appear, this is not so important. The only thing that is important is what kind of singularities are there and how do they depend on the variables. So I just want to briefly sketch the idea behind this. So in the beginning, we didn't integrate any variable yet, so we just have 1 over psi squared. The only singularity is psi. You can only have a singularity when psi vanishes. After one integration, so what happened after one integration? I'm not sure if I still have it anywhere. Oh, I still almost do. So after one integration, what are you doing? We did this, we just got 1 over psi upper 1, psi lower 1. So apparently we now have 2 potentially different singularities. So we have psi upper 1 and psi lower 1. And we also had I2 after 2 integrations, which was this combination. We had this denominator times a logarithm psi upper 1, lower 2, psi upper 2, lower 1, psi upper 1, 2, psi lower 1, 2. So here we have singularities when either of these polynomials vanish. But the important point is that the set of singularities, if you reduce this, then this was also a linear polynomial, right? Which I discussed earlier. So this d was squared. So also in this case, the prerequisite is actually fulfilled, that all the potential singularities are linear in the next integration variable. Now, if you want to understand Feynman diagram and all the amplitudes that we might associate to this diagram, it is enough to just look at these polynomials and how these singularities develop when you integrate out more and more variables. So there's a name for this, which is something that Francis introduced under the so-called polynomial reduction, which is very interesting and it's very important. But of course, I only have 5 minutes left. So I'll just say to you that there are algorithms under the name of polynomial reduction to compute upper bounds on these sets of singularities. They actually have a name, they're called Landau varieties. And the bottom line is that once one has understood this polynomial reduction for a particular graph, one knows that all the amplitudes one could associate with it will be, via this algorithm, expressible in terms of multiple polylogarithms of a particular type. So note, the actual integrand does not matter. By which I mean we can take any integrand which is compatible with these singularities we started with. So if you compute a polynomial reduction for this graph just with the first semantic polynomial, then we can also make statements about integrals, generalized integrals of this form. There we have omega g, but we raise psi to some higher power a, and we put some polynomial in the numerator, so such that everything is homogeneous. Or more generally, even though I restricted to the one scale case, we can also look at general Feynman amplitudes, where we can also have such a polynomial, but now allow for both graph polynomials, the psi and the xi polynomial, raised to arbitrary integer powers, subject only to the condition that it is a well-defined projective integral. So in this case, we start with a variety which contains both polynomials. Which in general makes things more complicated. In particular, if you have a graph where every edge is massive, then you know that the xi polynomial is quadratic, and you actually do not get very far. But there are many applications, for example, without masses or just with few masses, where you can still play the same game and get statements which are valid. So I don't have time to explain this algorithm, but I want to explain to you what the outcome of this techniques is. So we have reduced the study of the actual amplitudes and the integrals to an algebraic or geometric task of understanding how these sets of polynomials which describe the singularities, how they behave. And so we have the amplitudes ig, which of course come from the graph. But somehow we take a detour, we make things more complicated. In order to understand the amplitude, we understand something much more complicated. We study how these partial integrals depend on all the Schwinger parameters. Yeah? So here we have a chain, how we get here via these integrals, partial integrals, k plus 1 up to n. And in case of kinematics, they also depend on q and m. But we do not even need to know anything about these explicit functions. We only need to know the places where they could have singularities. So actually, we get information about these by looking at these sets of polynomials. And if you want to understand this sequence of singularities, you will have to take care of these resultants, of these Dodgson identities, which I mentioned earlier. The point is that they do not appear always, but they depend on the combinatorial structure of the graph. So the question whether such a denominator you get from partial fraction decomposition is linear, factorized into linear factors, is something which relates to combinatorial structures in the actual graph. Yeah, so here the graph feeds into as well. And the bottom line is that you can get statements like the one Francis briefly mentioned. So there's a theorem by him. Let G have vertex with, or actually I will give another example because I have 1 minute left only. Consider the family of ladder boxes. So these are the integrals with 4 external legs, but you can make them arbitrarily big. And you can make 2 legs massive on the side. So you can have a triple box. This is what would be called a triple box. And you can have arbitrary n-uple boxes with 2 massive legs. So we have an infinite family of Feynman graphs. Then if G is such a graph, then the actual amplitude associated with this graph as a function of the 4 momenta with these side constraints is a multiple polylogarithm. And you can actually say what kind of multiple polylogarithm. So you can write down an upper bound on the differential forms which make up this iterate integral. Or in other words, you can specify what the arguments of this multiple polylogarithm can be in the worst case. And there's another class of graphs which Francis studied, which are vertex with 3 graphs. So the idea is that those contain graphs, for example, with 3 external vertices, like these things. And again, you can generalize this to have 3 external momenta. And because these graphs have a very special combinatorial structure, they're very rigid, you can use this structure to prove factorization identities of these Dodgson polynomials, which then tells you that the actual amplitude is a multiple polylogarithm of a particular type. And in practice, you can also use this to do explicit computations. So I want to end here, and thank you for your attention. And yeah, thanks.
Okay, any question?
What happens if the dimension D is odd and I have square roots?
Yeah, I don't say anything about odd dimensions. I'm sorry for that.
In the various tool you have mentioned, specifically in your example when you start with, you use the contraction of line to have some vertices and to remove line, and then you get also these Landau varieties. And it's exactly what we use as physicists when we try to factorize some processes when you have 2 scales. So, for example, you have 2 scales, okay, and you want to investigate how certain class of diagram can be factorized in order to describe the confinement part and the hard part, okay? And that's explicitly what most of people involved, not in exact computation, but in a factorized form for high energy, do every day.
So that's an expansion in like...
To try to get asymptotic, to even get the power expansion, like what we call twist expansion in QCD. So does all this machinery could say something interesting on this?
Well, I think so. Essentially what you're doing whenever you're doing an asymptotic expansion like this on other cases, I mean, in physics there's this whole business of expansion by regions, for example, where you just take an individual Feynman diagram and look at an expansion where some momentum gets big or some mass gets big, or you're doing this kind of thing. You're always doing, in this picture it has a unified interpretation in some way, because you look at this integral which is made up of this psi polynomial, and here in this polynomial you have your different masses and momenta. Now you're looking at what happens when one of those dominate and the others. So essentially you would hope that you can expand the integrand in this limit and then just compute the integrals themselves. And the only problem is that if you do this expansion you might introduce new divergences which you might have to take care of. But if this is not the case, then you're right. So you're using in this case a factorization of this polynomial in this particular kinematic limit. What I did here is that I looked at a factorization of the psi polynomial, which does not involve any kinematic invariance. But you also have factorization polynomials for the psi polynomial, and they are all very important also in the motivic approaches that were mentioned today. So yeah, I mean, it's certainly very much related. What you also realize immediately when you do this is that when you do such an expansion, you simplify the situation drastically, because you replace this complicated bit by a product of two much simpler polynomials. And then essentially the polynomial reduction also breaks down into two independent pieces because the variables separate somehow. So yeah, so we do have cases where, for example, in such an expansion, everything is linearly reducible and you can compute the coefficients in terms of multiple polylogs, whereas for the full actual function it's much more complicated and you do not know what happens. So this is also one approach to try to get closer to something very complicated which you don't understand.
A question?
Can I ask? In the same spirit. So if you have a gauge theory, okay, you have of course sum of many diagrams, and each individual diagram produces you some, let's say, power of hard scale or whatever, okay, which has completely nothing to do with if you perform summation. So do you have some clever way to treat numerators, okay, in parametric representation, to combine, okay, somehow?
I must say no here. Of course, the hope is that there should be something and you would hope to find, but so far, as I'm aware, there have been some attempts, but it is not yet clear how to do it. The problem is that you have all these integration by parts relations. So in the ideal world, you could just take the representations for different diagrams with their numerators and put them all in one numerator and look at this integral in one go. And then you would hope that you see the cancellations of the leading degrees or whatever. The problem is that even though this is a sort of canonical representation for a diagram, it's not the unique one because you have all these integration by parts identities. So you can imagine situations where you take a sum of two terms and they don't look, that there are no visible cancellations at all, but when you do partial integration or write in a different form, then they are manifest, and then it's easy. So I know that some people have tried this in other applications to try to combine different diagrams and see why certain cancellations happen in gauge theories. But as far as I'm aware, this is still very much work in progress, and we don't yet know the right approach for this. The problem is really that the representation is not unique, and you would need a way to find the right representation in order to see it easily. So, but probably finding that representation is as complicated as solving the problem. So.
What you have done here was not a change of representation. I mean, the steps of your computation, you see it as a change of representation.
You mean change of variables, or?
Yes, I mean all the steps which you transform the integral of.
Yeah, but I only look at one integral at a time. Yes. Yeah, and I'm changing, that's right, I'm changing the representation of my I don't change the function, I just rewrite it in a different way, which makes it essentially trivial to compute the integral in this new representation. So this is the whole point. What I should mention briefly is that, of course, this is a very simple-minded approach in the sense that I just take the Schwinger parameters, which are 50 years old or 60 years old at least, and try to do the integral in these variables. And it's sort of Alice's wonder that we actually get very far in many cases, but we also have counterexamples where we know that an integral is a multiple polylogarithm, but we do not see it in this way because it's not linearly reducible. So you can have situations where something looks very complicated, but it's just a sign that actually these variables are the bad variables. And of course, all physicists know that it's extremely important to find the right variables. I mean, also for tree-level amplitudes, if you want to be efficient in writing them down. And here you have a similar situation in the integration process. It's, of course, absolutely unclear what the perfect representation in each case would be. So this is a completely open field, I would say, at the moment. And there are many different ideas one could try out and try to follow. But I can just say at the moment there are examples, many examples, where we have to twist this representation, go to another representation, do some changes of variables. And then it's clear that it's a polylogarithm or something related, but not in the original variables. Yeah.
Well, for the formula with the general polynomial p, I think in some cases that I know integration by part enabled to transform this into another form with different a and b. It's more or less what we have seen in the previous talk.
Yeah, so there are certainly tons of relations here, right? But the problem is, I mean, the question that came earlier was if you have different integrals and you want to combine them and see that there are some cancellations.
Yeah.
If you bring them in if you select some master integrals and write everything in terms of these master integrals which are independent, then you should see it on that form. But it's not necessarily manifest in the in this canonical representation.
If you bring them using
yes.
if you manage to get to master integrals, it might be easier. And the main trick is integration by part in this case, as we have seen.
Yes.
And I know other examples of integration by part gives a result.
A question here, you computed the residue. I mean, in the example you gave, you computed the residue, but can you compute the rest of the epsilon expansion, at least the constant term?
Well, for this integral, I mean, it has been computed, I think, 2 or 3 years ago in the on-shell massless case. I mean, the problem is always what are the kinematics that you do. So if you look at the wheel with 3 spokes, and you just look at it as a 3-point function, so you put one momentum to 0, but take the other 3 momenta as arbitrary, then it's in this class of vertex with 3 graphs. I didn't have time to describe these, but this function you can compute explicitly in terms of multiple polylogarithms to all orders in epsilon, close to all even dimensions, with arbitrary powers on the propagators. As soon as you go to 4 off-shell external momenta, I don't even know what the right representation for the kinematics is. I mean, even if you take the one-loop box with 4 off-shell momenta, it is only known in 4 dimensions. But if you go to 4 minus epsilon dimensions, you don't really know what to do, because it's just the kinematics is too complicated. So the only case I know where this is computed with 4 external momenta is also cheating, because it puts all 4 external momenta on shell. So it's only a function of 2 variables. And then it was computed by Hen and Smirnov, and it was shown to be a multiple polylogarithm. And this is actually one of these examples where, when you do it with the Schwinger parameters, you do not get linear reducibility in the sense that I mentioned here. So at some point, after one integration, you have a quadratic polynomial. So it seems mysterious, but then there's a change of variables which you can do, which makes this thing factorize, and then you can apply the algorithm, and you see you get this. But it's one of the examples where I would like to have a better reason to see why it's a polylogarithm or not. But yes, you can compute higher orders in the epsilon expansion. The reason is that when you go to, so the epsilon sits here, right, in these exponents. So if you do an expansion in epsilon, the only thing you do is that you introduce logarithms of the polynomials, which are, of course, in the space of iterate integrals over these polynomials that I start with anyway. So this is the statement that here, the actual integral doesn't really matter. So I can allow for arbitrary powers, but I can also expand in the powers and allow for logarithms. You can also have logarithms of individual Schwinger parameters in the game and arbitrary powers of those. This does not play any role for the function theory. Of course, it makes in practice the computation more complicated and takes more time, but it does not change conceptually what happens to the integral.
So if you have a linear reducibility, without these logs, if you add the logs, you're saying that you still keep this property?
Yeah. So I was quite sloppy actually with the way how I defined linear reducibility. So I didn't even mention the name, did I? At least I didn't dare to write it down. Okay. Yeah, so the idea is that it's really just something depending on the polynomials. So you take the polynomials, and then you see what is the worst case that could happen. If I take an arbitrary, so you do not exactly do not want to look at the actual integral. Just take whatever integral which only has these singularities. Do one integration. What are the singularities that I could have here? And then by quite general arguments, just by looking at the vibration of this variety, you can prove these things, that these sets are upper bounds on the singularities. I mean, I hope I made somehow clear how this actually arises in the computation, because what happens if I want to compute such an integral? Well, this is a logarithm, so it is clear how to write it in this hyperlogarithm form. And the letter I get here, this here is psi upper 1 alpha 1 plus psi lower 1. So the letter will be something like, will be some L omega. The 0 is at psi lower 1 divided by psi upper 1. So after the integration, I have, of course, singularities when these go to 0. I will have to do the partial fraction decompositions, but these are all taken care of by D. So the changing the powers or anything changes the actual representation at the point, but it does not change the fact that it is a hyperlogarithm with these as an upper bound of the letters and denominators which appear. So this is the point. In a way, you make it more complicated because you have to look at things depending on all these Schwinger parameters, which are completely unphysical, of course, which only appear in the very last step when you did the last integration. But on the other hand, you abstract from the actual integrand and you look at all amplitudes which you can assign to this graph at the same time, because this is something which only depends on this geometry of the graph hypersurfaces.
All right. More question? Okay, thank you.